In the fall of 1943, a machine running on Factory Street in Rockford, Illinois, had never seen the aircraft it was helping to build. It never would. The machine was an Ingersoll transfer line, a chain of 12 cutting stations linked by an automated conveyor, each station removing a precisely calculated amount of metal from a cast iron blank, moving through at a rate no human hand could match and no single machine could sustain. At the end of the line, what had entered as a raw casting emerged as a finished crankcase for the Wright R3350 duplex Cyclone, the 18-cylinder 2,200 horsepower engine that would power the B-29 Superfortress over the Pacific. The tolerances on that crankcase were held to 2 10,000ths of an inch, not 2 thousandths. 2 10,000ths, a dimension smaller than the width of a human hair, held across a cast iron surface the size of a kitchen table, repeated 500 times per 8-hour shift by a machine that did not know what it was making and did not need to. The machine that held those tolerances was designed in Rockford, Illinois, built in Rockford, Illinois, shipped from Rockford, Illinois by men who would spend their careers building things they would never fully see the purpose of and who understood in the way that skilled industrial workers understand things that the purpose was not theirs to see. Their job was the tolerance. The tolerance was the point. By 2001, the company that built that machine no longer existed. The name Ingersoll had been sold. The Factory Street plant had gone quiet. The 4,000 men and women who had worked 3 shifts a day through the war years, through the post-war boom, through the golden decade of American automotive manufacturing, were gone. Rockford, Illinois, the city that had produced more machine tools per capita than any city in America at the height of its power, was reckoning with what a Rust Belt city reckons with when the last plant closes and the county employment office runs out of forms. A decade before the end, Ingersoll had been the company that every major American automaker called when they needed to retool a plant. General Motors, Ford, Chrysler. When they needed a system, not a machine, a system capable of taking a raw casting in one end and delivering a finished engine block out the other without a human hand touching the metal between stations, there was one American company whose engineering staff could design it, whose factory could build it, and whose installation teams could commission it and hand it over to production running at rated cycle time. That company was Ingersoll. But the real story of Ingersoll Milling Machine is not the story of a company that failed to compete. It is the story of a manufacturing philosophy. The American belief that precision at scale achieved through specialized machinery engineered for a single purpose and built to last 20 years was the foundation on which industrial civilization rested. And what happened when the market decided it was wrong? Every week on this channel, we tell the stories of the American companies that built the machines the factory ran on and what the market did to them. If that history matters to you, like the video and subscribe. We have a long list to get through and the stories do not get easier. This one begins in Rockford, Illinois. In 1887. Rockford, Illinois in 1887 was not yet the machine tool capital of America. It was becoming one. And the difference mattered because what a city is becoming shapes the kind of company that takes root in it differently than what a city already is. The Rock River ran through the center of town. The Chicago and Northwestern Railway ran through its industrial districts. Swedish and Norwegian immigrants who had come to work the furniture factories and the farm implement shops had brought with them a tradition of precision metalwork that preceded the machine tool industry itself. A cultural inheritance of hand skills of fitting and scraping and measuring that the American Midwest was absorbing and converting into industrial capacity at a rate the Eastern Seaboard manufacturing cities could not match. Rockford had iron. It had rail access. It had men who knew how to work metal. What it did not yet have was a company that could translate those assets into something the American factory had never been offered before. Leander Ingersoll founded the Ingersoll Milling Machine Company on Factory Street in 1887. He was a machinist by trade, trained in the Illinois River Valley tradition of practical mechanical engineering, the tradition that built farm equipment and river machinery and the early infrastructure of a continent that was still being assembled. He had watched the American factory floor long enough to understand its central problem, and the central problem was not precision. American machinists had precision. The central problem was repeatability at volume, the ability to produce not one correct part, but 10,000 correct parts to the same dimension at a cost per unit that made mass production economically possible. The machine tool of Leander Ingersoll's era was by design a general-purpose instrument, a milling machine, a lathe, a drill press. Each was operated by a skilled machinist who set up the work, made the cut, measured the result, and moved to the next piece. The skill was in the man. The machine was a platform for that skill. And for a century of American manufacturing, that relationship had been sufficient. It was no longer sufficient. Henry Ford had begun to make clear in the decade before Ingersoll's founding, and in the decades immediately after that, the future of American manufacturing was not skilled machinists producing parts one at a time. It was systems producing parts continuously one after another, without interruption, without setup time between pieces, without the accumulated variation that even the most skilled machinist introduced when he repositioned a part by hand. Ford did not need better machinists. Ford needed a machine that did not require a machinist between parts. What the American factory floor was missing in 1887 and in 1900 and in 1910 was a transfer line. A transfer line is not a machine in the sense that a milling machine or a lathe is a machine. It is a system, a series of machining stations linked by an automated conveyor that moves the workpiece from station to station without human intervention. Each station performs one operation. A drilling head bores a specific set of holes to a specific depth. A milling head removes a specific surface to a specific flatness. A tapping station threads a specific set of holes to a specific pitch. The workpiece arrives at each station in the same orientation, held in the same fixture, located to the same datum surfaces every time, because the fixture does not change between pieces and the conveyor does not deviate. The variation that a skilled machinist could not prevent when repositioning a part by hand was eliminated not by improving the machinist, but by removing the repositioning. Ingersoll did not invent the concept, but Ingersoll was the first American company to engineer it at the scale and precision that the American automotive industry required, and to build the organizational capability to design, manufacture, and install custom transfer line systems for customers whose production requirements were unlike anything the machine tool industry had previously been asked to solve. The first major transfer line Ingersoll delivered to the American automotive industry went to Ford's River Rouge complex in Dearborn, Michigan in the early 1920s. The contract value was in the range of $800,000 to $1.2 million, the equivalent of $13 to $18 million today. It was not sold through a machine tool dealer. There were no machine tool dealers who handled equipment of this scale and complexity. Ingersoll's engineering staff went directly to Ford's plant engineers, designed the system to Ford's production specifications, built it on Factory Street, and installed it in Dearborn with Ingersoll's own installation crews. That model direct engineering engagement, custom design factory, build factory installation was not a sales strategy. It was the only way the product could exist. A transfer line was not a catalog item. It was an engineered solution to a specific production problem, and no two were identical. The engineering knowledge required to design one correctly lived inside Ingersoll's staff. It could not be purchased from a distributor or reverse engineered from a competitor's catalog because no competitor's catalog contained it. American Machinist magazine covered the River Rouge installation as a milestone in American production engineering. The Thomas Register of American Manufacturers listed Ingersoll under a category that had effectively one entry. By the late 1920s, when General Motors began its first major plant expansion under Alfred Sloan's divisional production system, the call went to Rockford. At its peak, the Factory Street plant employed approximately 4,000 workers across engineering, manufacturing, and field installation. They were not interchangeable with the workforce of any other machine tool builder in America because the work they did not exist anywhere else in America. That was Ingersoll's advantage. It was also, as the story will show, the precise nature of its vulnerability. But in 1932, none of that was visible yet. In 1932, Ingersoll was about to build something that would define American manufacturing for the next 50 years and put an 8-cylinder engine under the hood of every American who could afford one. In the spring of 1932, Ford Motor Company had a problem. Henry Ford had promised the American public a V8 engine in a car priced for the working man. The engineering was solved. The metallurgy was solved. The problem was production. A V8 engine block, 8 cylinders arranged in 2 banks of 4, cast as a single iron unit, was among the most geometrically complex castings the American automotive industry had ever attempted to machine at volume. It required more than 400 individual machining operations, drilling, boring, milling, tapping, reaming each, to tolerances that the engine's performance depended on, each to be repeated on every block that came down the line at a production rate that made the Ford V8 affordable at the price Ford had publicly committed to. No single machine could do it. No team of machinists working individual machines could do it at the volume Ford needed at the cost Ford required with the consistency Ford's tolerances demanded. Ford called Rockford. The transfer line that Ingersoll designed and delivered for the Ford V8 engine block was unlike anything the American factory floor had seen. It ran more than 60 feet from end to end, longer than the distance from home plate to first base on a regulation baseball diamond. It weighed in total over 200 tons of cast iron precision ground steel and hardened tooling. It contained 15 machining stations, each equipped with custom-designed spindle heads, the rotating assemblies that held and drove the cutting tools, positioned to engage the casting at angles and depths calculated specifically for that one engine block and no other. At each station, the block was located, positioned, and clamped in a fixture. A precision-machined iron casting that held the workpiece against 3 datum surfaces, ground flat to within 0.005 of an inch per foot, so that every block arrived at every cutting tool in exactly the same position as every block before it. The fixture did not adjust. The conveyor did not vary. The spindle head did not compensate for human judgment. The system assumed that if every input was controlled, every output would be correct, and it was right. The cycle time was 48 seconds per station. 15 stations. 1 block entering the line every 48 seconds. 500 finished engine blocks per 8-hour shift. At $12 million for the complete installation, the equivalent of approximately $260 million today, the Ford V8 transfer line was not a machine tool purchase. It was a capital infrastructure decision of the same order as building a new foundry or acquiring a stamping plant. A senior Ford machinist in 1932 earned approximately 75 cents an hour. The transfer line cost more than 8 million hours of that machinist's labor. Ford signed the contract because the arithmetic was not close. The transfer line would pay for itself in reduced labor cost within 4 years of operation, and it would run for 20. No Japanese machine tool builder could have offered an equivalent system in 1932. No German builder, no British builder. The engineering knowledge to design a 15-station transfer line for a V8 engine block, to calculate the cutting forces at each station, to design the fixture datums, to specify the spindle-bearing preloads that would hold tolerances across 3 shifts a day for 2 decades existed in one place on Earth. It existed on Factory Street in Rockford, Illinois, in the heads of Ingersoll's engineering staff, and in the accumulated drawings and process records of 30 years of custom transfer line work. That was Ingersoll's moat, not a patent, not a price advantage, not a distribution network. Knowledge-specific, accumulated, non-transferable knowledge that no competitor could acquire without building the same history that had produced it. The Ford V8 went into production in the spring of 1932. It was priced at $460 for the base model, the first V8 automobile available to American working families at a price they could consider. Within 2 years, Ford had sold over 1 million V8-powered vehicles. The engine that made that possible was machined on an Ingersoll transfer line in Dearborn, Michigan, running at 500 blocks per shift, holding tolerances that Ford's own engineers had initially questioned whether any machine system could maintain. General Motors ordered its first Ingersoll transfer line for the Chevrolet engine plant in Flint, Michigan, before the Ford installation was complete. Chrysler followed within 18 months. By 1936, every major American automotive engine plant was either running Ingersoll transfer line equipment or waiting for a delivery slot on Ingersoll's Factory Street production schedule. The institutional endorsement list was not assembled over decades. It arrived in a single decade because the Ford V8 contract was not a reference sale. It was a demonstration visible to every plant engineer in the American automotive industry that Ingersoll had solved a problem the industry had not known how to state precisely until Ingersoll stated it for them. The problem was this: precision at volume achieved through a system engineered for one purpose was worth more than flexibility achieved through general-purpose machines operated by skilled men. When the part was complex enough, and the volume was high enough, and the tolerances were tight enough, the transfer line did not merely outperform the alternative. It made the alternative impossible. The nameplate on the transfer line's main frame read, Ingersoll Milling Machine Company, Rockford, Illinois. In every engine plant that ran one, that nameplate was not a city of origin. It was a production guarantee. The Ford 5.8 contract had done something that no amount of advertising in American Machinist magazine could have accomplished. It had made Ingersoll's capability legible to every plant engineer in American industry, not as a promise in a catalog, but as a running system in a production plant that anyone with sufficient credentials could visit, observe, and measure against their own production problems. The visits came. Through the late 1930s, Ingersoll's Factory Street engineering staff was simultaneously designing transfer line systems for General Motors engine plants in Flint and Pontiac, Michigan, for Chrysler's Dodge main facility in Hamtramck, Michigan, for the Studebaker Corporation's South Bend, Indiana engine plant, and for a growing list of non-automotive industrial customers who had read the Ford V8 story in American Machinist and understood that the transfer line principle was not limited to engine blocks. Any complex casting produced in sufficient volume at tight tolerances was a candidate. Ingersoll's engineering staff was prepared to make that case in any plant engineer's office in America, backed by a reference list that was growing faster than any competitor could read it. By 1940, Ingersoll had delivered more transfer line systems to American industry than all other builders combined. That was not a marketing claim. It was an arithmetical fact because no other builder had the engineering staff, the factory street manufacturing capacity, or the installation crew infrastructure to compete at Ingersoll's volume and complexity. Rockford was not merely the location of Ingersoll's factory. Rockford was the reason Ingersoll's factory could exist. The Swedish and Norwegian machinist tradition, the iron casting suppliers in the surrounding counties, the apprenticeship pipeline from the Rockford Public School, vocational programs that fed trained hands into Factory Street year after year. Then the war came, and Ingersoll became something larger than a machine tool builder. In the spring of 1940, the United States Army Air Corps, soon to become the Army Air Forces, began the largest military aviation procurement program in American history. The targets were staggering 96,000 aircraft in 1944 alone, more than the combined production of Germany, Japan, and Italy. Every aircraft in that program required engines. Every engine required a machined block, a machined crankcase, a machined cylinder head. Each held to tolerances that flight safety demanded and that no individual machinist working a conventional machine tool could maintain across the production volumes the program required. The Army Air Force's procurement office knew where to call. Ingersoll received contracts for wing spar milling machines for the Boeing B-17 Flying Fortress program, massive horizontal milling systems designed to hold the aluminum wing spar, the structural backbone of the B-17's wing, to a flatness of 0.002 inches over a length of 30 feet. A wing spar that deviated from flatness by more than that specification would affect the aerodynamic characteristics of the wing under load. At altitude over Germany with a full bomb load and anti-aircraft fire coming up from below, the consequences of a spar machined out of tolerance were not theoretical. Ingersoll built the machines that held the tolerance. Boeing built the aircraft that flew on it. The Wright Aeronautical Corporation's plant in Paterson, New Jersey, ran Ingersoll transfer line equipment to produce the crankcase and cylinder head components for the Wright ER-3350 duplex Cyclone, the 18-cylinder radial engine that powered the B-29 Superfortress. The R-3350 was the most powerful aircraft piston engine in American production during the war, and it was among the most dimensionally demanding. The crankcase alone required more than 300 individual machining operations held to tolerances that the engine's bearing clearances measured in 10,000ths of an inch made non-negotiable. A crankcase bored 2 10,000ths out of specification would produce an engine with premature bearing wear. An engine with premature bearing wear on a B-29 at 30,000 feet over the Pacific was not a maintenance problem. It was a mission abort or worse. The Ingersoll transfer line running at Wright Aeronautical's Paterson plant in the fall of 1943 produced the crankcase for the Wright R-3350 duplex Cyclone, the engine that powered the B-29 Superfortress. The tolerances on that crankcase were held to 2 10,000ths of an inch. The machine that held them was built in Rockford, Illinois, by men who would never see the aircraft it helped put in the sky. At the American Car and Foundry plant in Berwick, Pennsylvania, Ingersoll equipment machined the turret ring, the precision-bored circular track on which the M4 Sherman tank's turret rotated for the primary American medium tank of the war. The turret ring required a bore diameter held to within 1/1000th of an inch across a circle 36 inches in diameter. Out of specification, the turret would bind under the lateral forces of combat movement. Ingersoll machined 49,000 turret rings for the Sherman program between 1942 and 1945. The Army Ordnance Corps did not record a single rejection on dimensional grounds attributable to Ingersoll equipment. The Factory Street plant ran 3 shifts 7 days a week from December 1941 through August 1945. Employment reached approximately 4,000 workers at peak engineers, machinists, assemblers, installers, and the drafting room staff whose drawings translated production requirements into machining systems that had never existed before and would never be built again in exactly that form. Each transfer line was a custom solution. Each drawing set was unique. Each installation was a field engineering problem solved by Ingersoll crews working in defense plants under production schedules that did not accommodate delays. Rockford in 1943 was a city running at the limit of its productive capacity, and the limit was considerable. What none of those 4,000 workers on Factory Street could see, what no plant engineer ordering an Ingersoll transfer line for a post-war automotive expansion could see, was that the same characteristic that made the transfer line irreplaceable was the characteristic that would eventually make it vulnerable. A transfer line engineered for one engine block could not be retooled for a different engine block without an engineering effort approaching the cost of a new system. It was precise because it was fixed. It was productive because it was specialized. And specialization in a market that was about to begin changing faster than any fixed system could follow was not only a strength, it was a debt coming due. The post-war decade was the best Ingersoll had ever seen, and it arrived without interruption. American soldiers came home in the fall of 1945 to a country whose industrial capacity had not been bombed, whose machine tool factories had not been converted to rubble and then rebuilt from foreign aid, and whose automotive industry was preparing to do something it had been unable to do since 1941, build passenger cars for American families who had spent 4 years saving money and waiting. The pent-up demand for American automobiles in 1946 was not a market condition. It was a geological pressure, and when it released into the largest sustained automotive expansion in the history of the industry. General Motors alone opened or retooled 11 engine plants between 1946 and 1955. Ford retooled its Dearborn and Cleveland engine facilities twice in the same period. Chrysler expanded its Trenton, Michigan engine plant to a capacity that required 4 new transfer line systems, all delivered from Rockford. The overhead valve V8 engine introduced by Cadillac and Oldsmobile in 1949, adopted by Chrysler in 1951, by Ford in 1954, and eventually by every American automaker, was a more complex casting than the flathead Fob 8. It replaced with more machining operations, tighter bearing tolerances, and higher surface finish requirements on the combustion chamber walls. Every additional complexity was an additional argument for the Ingersoll transfer line. Every tighter tolerance was a reason to call Rockford rather than attempt the work on general-purpose machines. Every new engine program at every Big Three plant began with an engineering conversation between the automaker's production engineers and Ingersoll's application staff. A conversation that typically ended with a contract and a delivery schedule measured in months, not weeks, because what Ingersoll was building could not be rushed without compromising the engineering that made it worth building. Through the 1950s and into the 1960s, Ingersoll's Factory Street plant was running at a pace that the post-war expansion had established as normal, and that the American automotive industry's relentless product cycle was sustaining. A new engine every 3 to 5 years from each of the Big Three divisions meant a new transfer line every 3 to 5 years from each of those plants, and the Big Three had collectively more than 30 engine manufacturing facilities in operation by 1960. The arithmetic was straightforward. The order book at Factory Street was never empty. The aerospace programs of the same decade added a dimension to Ingersoll's work that the automotive contracts alone could not have provided. The Cold War defense build-up, the B-52 Stratofortress program, the Pratt & Whitney J-57 jet engine that powered it, the General Electric J-79 that powered the F-104 Starfighter and the B-58. Hustler required precision machining of jet engine components at tolerances that exceeded automotive standards by an order of magnitude. Jet engine casings, compressor discs, turbine housings. These were not cast iron engine blocks. They were titanium and high-temperature nickel alloys machined to millionths of an inch on equipment that had to maintain that accuracy across production runs measured in thousands of units. Ingersoll built the systems. The engineering problems were different from automotive transfer line work. The materials were harder. The tolerances were tighter. The production volumes were lower, but the underlying discipline was the same. Understand the workpiece, design the system around it, hold the tolerance every time. Ingersoll's engineering staff had been doing that since the Ford Vate contract. The jet engine contracts required them to do it at a level of precision that pushed the boundaries of what fixed-cycle transfer line machining could achieve, and they achieved it because the alternative was to tell the United States Air Force that the work could not be done in Rockford, and that was not an answer Factory Street was prepared to give. By the mid-1960s, Ingersoll Milling Machine Company was at the apex of everything it had been built to be. The Factory Street plant employed close to 4,000 workers. The engineering staff, the men who designed the transfer line systems, who calculated the cutting forces, who specified the fixture datums, who wrote the installation procedures, was the largest and most experienced concentration of transfer line engineering expertise in the world. Not in the United States. In the world. There was no other city, no other company, no other factory floor where the accumulated knowledge of 50 years of custom transfer line engineering existed at the density it existed on Factory Street in Rockford, Illinois in 1965. The machines Ingersoll built in that decade ran in plants that made the cars that filled American driveways, the engines that powered American military aircraft, the components that equipped American manufacturing at a scale the rest of the world was still measuring itself against. A machinist who had spent his career at Factory Street, who had learned to read a transfer line drawing to set up a fixture, to verify a spindle head's positional accuracy with a test indicator and a precision ground reference bar, possessed a professional knowledge that had taken decades to accumulate and that existed nowhere else in the same form. He was, without knowing it, one of the last practitioners of an American industrial art that was about to become unnecessary. Not because the work would stop. The engine blocks would still need to be machined. The tolerances would still need to be held. But the system that held them, the fixed transfer line engineered for one part running one cycle, producing one result with no capacity for variation, was about to meet a market that had decided variation was not the enemy. Variation was the point. Flexibility was the new precision. And flexibility was not something that Factory Street in 1965 had been built to deliver. The first indication arrived not as a crisis, but as a number. In 1965, Japanese machine tool imports into the United States totaled $28 million. By American Machinist magazine's annual inventory survey, that number represented less than 4% of total American machine tool consumption. It was a footnote. It was the kind of number that a Factory Street engineering manager reviewed in the NMTBA's annual statistical report, noted without alarm, and set aside in favor of the next delivery schedule on his desk. He should have kept reading. The number that should have kept the Factory Street engineering manager reading was not the $28 million in Japanese machine tool imports recorded in 1965. It was the trajectory behind that number, the rate at which it was growing, and the reason it was growing, and what the reason implied about the American machine tool market that Ingersoll had spent 80 years learning to serve. Japanese machine tool builders, Mori Seiki Yamazaki, Mazak Okuma Makino, had entered the American market in the early 1960s with a product category that did not exist in Ingersoll's order book and had never needed to. They were selling NC machining centers, numerically controlled machine tools that could perform multiple operations on a single workpiece without the workpiece being moved between machines, guided by a punched tape or digital code rather than by a machinist's hands. NC stood for numerical control, a system in which the machine's axis movements were directed by a program, not by a skilled operator turning handwheels and reading dial indicators. The first American NC machines had been developed at MIT under Air Force contract in 1952. By 1965, the technology had matured enough that Japanese builders were offering it in catalog form at prices that American job shops could consider without requiring a capital appropriation from a corporate board. Ingersoll did not sell NC machining centers. Ingersoll sold transfer lines. These were not competing products. A transfer line and an NC machining center were not alternatives to each other in the same way that a freight train and a delivery truck are not alternatives to each other. They move different volumes over different distances for different customers at different costs. A transfer line produced 500 engine blocks per shift. An NC machining center produced perhaps 12 complex parts per shift with the ability to change programs between parts and machine a different geometry on the next piece. The transfer line was volume. The NC machining center was flexibility. For the American automotive industry of 1965, running plants designed around fixed high-volume production of standardized engine families, flexibility was not what the production superintendent needed. Volume was what he needed. Ingersoll had volume, the Japanese had flexibility, and the market in 1965 was still organized around volume. What changed was not the technology. What changed was the market the technology served. The 1973 OPEC oil embargo did not merely raise gasoline prices. It restructured the American automotive market in a way that the industry's production infrastructure, the transfer lines, the engine plants, the stamping facilities had not been designed to accommodate. American consumers confronting gasoline at prices that had been inconceivable 18 months earlier began buying smaller cars in numbers that the Big Three had not forecast and were not equipped to supply from domestic production. The four-cylinder engine, which American automakers had largely abandoned in the 1950s in favor of the V8, returned to the American market not as an economy option, but as the primary powertrain for a new generation of vehicles that Detroit was being forced to develop under time pressure it had never previously experienced. A four-cylinder engine block required a transfer line. But it was not the transfer line that was already running in the Flint engine plant, or in the Cleveland engine plant, or in the Trenton engine plant, because those lines had been engineered for V8 blocks, and a V8 block and a four-cylinder block were not the same. Casting did not have the same machining requirements and could not be produced on the same system without an engineering effort that approached the cost of building a new line. The Big Three's investment in Ingersoll transfer line infrastructure, the infrastructure that had given them the highest volume engine production capacity in the world, was now a constraint. The precision and specialization that had been the point of the transfer line was now the problem with it. General Motors began cautiously at first, and then with increasing urgency, to ask a question that Factory Street had not previously been required to answer: could a transfer line be made flexible? Could a system engineered for one part be re-engineered at reasonable cost and in reasonable time to run a different part when the market required a different engine? The honest answer from Ingersoll's engineering staff was not easily, not cheaply, not quickly. A transfer line's fixture datums were machined for a specific casting geometry. Its spindle heads were designed for specific hole patterns and surface locations on a specific part. Its cycle time was calculated for a specific sequence of operations on a specific workpiece. To change the part was to change the system, and changing the system meant rebuilding it at a cost and on a schedule that compressed the economic advantage of the transfer line approach precisely when the market was under the most pressure to reduce capital expenditure. General Motors heard that answer in 1974. They began exploring an alternative. The alternative had a name: the Flexible Machining System. An FMS, Flexible Manufacturing System, used CNC, machining centers, computer-controlled conveyors, and automated workpiece handling to produce a family of related parts on shared equipment that could be reprogrammed between part numbers. The FMS did not match the cycle time of a dedicated transfer line on any single part. It could not. The physics of the situation-changing tools, repositioning fixtures, loading and unloading different castings, imposed a time cost that dedicated tooling eliminated. But the FMS could run 3 different engine block variants on the same equipment in the same shift, and when the market required a 4th variant, the reprogramming cost was a fraction of the retooling cost on a dedicated line. In 1975, Ingersoll recognized the threat clearly enough to attempt a response. The response was rational. It was well-engineered. It was too late. Ingersoll's engineering staff began developing large-scale CNC machining systems. Not the catalog NC machining centers that Mazak and Okuma were selling to American job shops, but heavy-duty CNC systems designed for the kind of large complex castings that automotive and aerospace customers required. The machines were impressive, the engineering was sound, but Ingersoll was attempting to enter a product dog category that Japanese builders had been developing for a decade, with controller technology. The Fanuc CNC controller, produced by a Japanese company that by 1980 controlled more than 50% of the world's CNC controller market, that Ingersoll did not manufacture and had no competitive alternative to offer. An American job shop in 1980 that was specifying a new CNC machining center was specifying a Fanuc controller. Not because Fanuc was the only controller available, because Fanuc was the controller that the shop's programmers already knew that the tooling suppliers had already written canned cycles for that the next machinist hired would already have been trained on. The Fanuc controller had become the programming language of American CNC machining, and Ingersoll, whose engineering heritage was in custom transfer line systems rather than in CNC controller development, had no entry in that language. The pivot that might have saved Ingersoll, an early committed investment in flexible manufacturing systems begun in 1972 rather than 1975, built around a CNC controller strategy rather than around the transfer line engineering heritage that had made Factory Street great, was not made. It is not certain that it could have been made in time. The organizational identity of a company that had spent 85 years engineering fixed, dedicated, high-volume production systems was not an asset in the development of flexible, reprogrammable, moderate-volume machining systems. The knowledge was different. The customer relationship was different. The sales cycle was different. The engineering culture was different. What Ingersoll had built on Factory Street was precisely suited to the American manufacturing market of 1955. It was becoming precisely unsuited to the American manufacturing market of 1980. And in 1979, the American manufacturing market of 1980 arrived early. In 1979, General Motors announced the X-Car program, the Chevrolet Citation, the Pontiac Phoenix, the Oldsmobile Omega, the Buick Skylark. Front-wheel drive, transverse-mounted four-cylinder engines. A fundamental architectural departure from the rear-wheel drive longitudinal V8 configuration that had organized GM's engine plant infrastructure since the 1950s. The X-Car program was not a niche product. It was GM's answer to the fuel economy crisis, designed to sell in volumes that would require full engine plant retooling across multiple facilities. The retooling call did not go to Rockford. GM's production engineering staff, working through the capital appropriation process for the X-Car engine plants, specified flexible machining systems for the new four-cylinder engine lines. The systems they ordered came from a list of suppliers that included Lam Technicon in Warren, Michigan, another American transfer line builder facing the same structural pressure as Ingersoll, and increasingly from European builders Comau of Italy, whose flexible manufacturing systems had been developed for Fiat's retooled engine plants in Turin, and Hüller-Hille of Germany, whose horizontal machining centers and FMS installations were equipped with Siemens and Fanuc controllers that American plant engineers were already comfortable specifying. The dollar figures tell the story with a precision that narrative cannot improve on. In 1978, Ingersoll's annual revenue from transfer line contracts with the American automotive industry was estimated at over $200 million. In 1982, that figure had fallen below $80 million. In 1986, it was below $40 million. The plants had not changed. The engineering staff had not changed. The Factory Street manufacturing capacity had not changed. What had changed was the order flow. And when the order flow changed in the transfer line business, it changed completely because transfer line contracts were not repeat orders for catalog products. They were one-time capital investments by customers who, once they had committed to a flexible manufacturing architecture, had no reason to return to a dedicated transfer line supplier. General Motors' market share fell from 46% in 1978 to 33% in 1986. Every percentage point of that decline represented engine production volume that did not need to be machined and transfer line capacity that did not need to be replaced. Ford's market share held somewhat better, but Ford's response to the fuel economy crisis included a component sourcing strategy that shifted increasing volumes of engine parts to offshore suppliers. Suppliers equipped with Japanese machining centers and European flexible manufacturing systems, none of which had been built in Rockford. Chrysler nearly ceased to exist. The federal loan guarantee that kept Chrysler operating in 1980 was not accompanied by a capital investment program for new engine plants. Chrysler's production engineering staff was managing survival, not expansion. The transfer line contracts that Chrysler would have placed with Ingersoll in a normal capital cycle were not placed with anyone. The three customers whose collective demand had sustained Factory Street's order book for 50 years were simultaneously contracting retooling away from dedicated transfer line architecture and, in one case, nearly liquidating. The timing was not coincidental. It was structural, the simultaneous arrival of the fuel economy crisis, the Japanese automotive competitive challenge, and the CNC technology transition in a market window of approximately 4 years from 1979 to 1983 that was too compressed for any fixed capital custom engineering business to navigate without fundamental restructuring. Ingersoll attempted the restructuring. The aerospace deepening that had been a supplementary revenue stream since the 1950s was accelerated. Ingersoll's engineering staff pursued contracts for large-scale CNC machining systems for Boeing's commercial aircraft programs, the 757 and 767, both entering production in the early 1980s, and for Lockheed and General Dynamics military programs that required the kind of large-format precision machining that Ingersoll's Factory Street capacity was suited to deliver. The aerospace work was real. The contracts were real. The engineering was by any measure among the most demanding that Factory Street had ever executed. But aerospace volume was not automotive volume. A Boeing 757 program required machining systems for an aircraft produced in the hundreds, not the hundreds of thousands. The capital value of an aerospace machining contract was substantial. The production volume it sustained at Factory Street was a fraction of what a single GM engine plant retooling had once provided. The workforce numbers record the arithmetic of the decline without editorializing. 4,000 workers at Factory Street in 1965, 3,200 in 1975, 1,800 in 1982, 900 in 1987. The reductions were not made in a single announcement. They came in increments: a layoff of 200 when a contract was delayed, a reduction of 150 when a program was canceled, a retirement not replaced when the order book did not justify the headcount. Each reduction was individually explicable. The cumulative pattern was a verdict. The engineering staff, the men who had designed the Ford 5.8 transfer line successors, who had engineered the B-29 crankcase systems, who carried in their heads the accumulated transfer line knowledge of 3 generations of Factory Street practice, left in the same incremental way. Some retired. Some were hired by Lam Technicon or by the European builders who were taking Ingersoll's contracts. Some left manufacturing engineering entirely. The knowledge they carried did not transfer to a successor institution. There was no successor institution. By 1990, Rockford's manufacturing employment had fallen by more than 60% from its 1965 peak. The city's unemployment rate, which had averaged 4% through the 1960s, reached 18% in 1983. One of the highest rates of any American city outside the primary steel towns. The Sunstrin machine tool plant, which had been Rockford's other major machine tool employer, had been acquired by United Technologies in 1974, and its machine tool division sold, renamed, and ultimately closed. National Twist Drill, another Rockford institution, was gone. The supplier network that had fed Factory Street, the iron casting shops, the precision grinding operations, the heat treating facilities contracted with it because their primary customer was contracting and their secondary customers were contracting for the same reasons. Rockford did not lose Ingersoll. Rockford lost the ecosystem that Ingersoll had anchored, and the ecosystem, once it began to contract, contracted faster than any of its individual members could have arrested alone. The end, when it came in stages that each felt like the last stage until the next one arrived. Ingersoll was acquired, restructured. The name was separated from the Factory Street operation. By 2001, the Ingersoll named the name on the transfer line that had held the Wright R3350 crankcase to 2/10,000ths of an inch in Paterson, New Jersey in 1943 had been sold to a German industrial group. Factory Street went quiet. The drawings remained. Somewhere, the knowledge did not. The machines Ingersoll built do not appear on eBay the way a Monarch 10EE toolroom lathe appears on eBay. listed by a retiring machinist in Ohio at $4,500, with photographs of the spindle nose and the serial number plate and the handwheel graduations, drawing inquiries from buyers in 4 states within the first week. A transfer line is not a machine that a retiring machinist owns. It is a machine that a corporation owns, and when the corporation retools or closes, the transfer line does not go to an estate sale. It goes to an industrial liquidator who sells the spindle heads and the fixture plates and the hydraulic power units as individual components to whoever can use them, and the conveyor structure and the guarding and the coolant systems go to the scrap dealer because there is no market for a 60-foot transfer line frame outside the production context it was engineered for. What survives of Ingersoll's work survives in pieces. In machine shops and small manufacturing facilities across the Midwest, individual spindle heads from Ingersoll transfer lines, the precision-assembled rotating units that held and drove the cutting tools at each machining station, have been mounted on custom bases and run as standalone drilling or milling units for work that their original designers never anticipated. They run because Ingersoll built them to run. The bearing preloads were specified for 20 years of 3-shift operation in an automotive engine plant. A small shop running one spindle head 8 hours a day, 5 days a week will not wear it out in a lifetime. The Ingersoll name is cast into the housing. The tolerances are still there. The Rockford Public Library holds one of the most significant collections of Ingersoll historical material, outside a corporate archive. Photographs of the Factory Street plant at peak capacity, wartime production records, engineering department group photographs from the 1940s and 1950s, and a partial collection of American machinist articles covering Ingersoll installations from the 1920s through the 1970s. The collection exists because a Rockford librarian understood in the early 1990s that the company's records were at risk as the organization contracted and made the institutional effort to preserve what could be preserved before it dispersed. It is not a complete record. It is what survived the gap between institutional decline and institutional memory. The Vintage Machinery website, vintagemachinery.org, holds scanned copies of Ingersoll catalog pages and technical documentation that collectors and industrial historians have contributed over the years. The material is fragmentary. Ingersoll did not produce the kind of retail catalog that a Brown & Sharp or a Cincinnati Millicron published for its standard product lines because Ingersoll did not sell standard products. What exists in the Vintage Machinery archive are engineering brochures, installation photographs, and the occasional technical specification sheet that a plant engineer had filed and that his successor had not discarded when the plant retooled. The Practical Machinist Forum, practicalmachinist.com, contains threads about Ingersoll equipment that read differently from the threads about Monarch lathes or Bridgeport mills. The Monarch threads are written by men who own the machines who are diagnosing a spindle bearing or sourcing a replacement apron gear. The Ingersoll threads are written by men who worked at the plants that ran the transfer lines, who remember the sound of a line running at full cycle, who remember the feel of setting up a fixture and verifying the datum surfaces with a test indicator before the shift started, who are looking for someone else who remembers the same things. They are not threads about maintenance. They are threads about memory. The Smithsonian National Museum of American History holds documentation of Ingersoll's wartime production contributions, the B-17 wing spar milling machines, the B-29 engine component transfer lines as part of its American industrial history collections. The machines themselves are too large and too application-specific to be preserved as artifacts in the way that a Monarch 10EE or a Brown & Sharp universal milling machine can be preserved. What the Smithsonian holds is the record of what the machines made possible, the production volumes, the tolerance achievements, the engineering decisions that allowed American aviation manufacturing to reach the output levels of 1944. The professional categories that Ingersoll's existence had sustained did not survive its decline in any transferable form. The transfer line engineer, the man who could take a customer's casting drawing, analyze its machining requirements, design a 15-station transfer line system around those requirements, specify the fixture datums and the spindle head configurations and the conveyor timing, and hand the completed design package to a manufacturing floor that could build it. That professional category no longer exists in the United States as a practice discipline. There are engineers who understand the principles. There are no engineers who have spent 20 years doing it because there has been no American institution doing it for 20 years to employ them in. The transfer line installation specialist, the man who could arrive at a customer's plant with an Ingersoll installation crew commission, a 12-station automotive transfer line, bring it to rated cycle time, verify its dimensional output against the engineering specification, and hand it over to production. That professional category is gone in the same way. Not retired, discontinued. The work itself ceased to exist in America before the last practitioners had finished their careers. The fixture designer, the multi-spindle head specialist, the transfer line application engineer who could walk a production superintendent through the capital justification for a $12 million system and leave the meeting with a signed letter of intent. These were American professional identities with apprenticeship pipelines and professional associations and 40-year careers. They did not transition into equivalent roles in flexible manufacturing or CNC programming. The knowledge was too specific, the institutional context too particular, the market for the skill too completely eliminated to permit a graceful professional migration. They were made obsolete by the same forces that made Ingersoll obsolete. And unlike the machines, they left no components behind that a small shop could mount on a custom base and run for another 30 years. Here's what the history books do not emphasize about the Ingersoll story and should. The transfer line principle that Ingersoll perfected on Factory Street in 1932, the automated sequential machining of complex castings through a series of fixed stations, each performing one operation in a controlled sequence, is still the production method for every internal combustion engine block manufactured anywhere on Earth today. The Toyota engine plant in Georgetown, Kentucky, the BMW engine plant in Spartanburg, South Carolina, the Honda engine plant in Anna, Ohio. Every one of those facilities runs transfer line equipment, automated computer-controlled, equipped with CNC spindle heads and programmable fixtures that Ingersoll's 1940s engineering staff would not have recognized in their specific implementation. But the principle: the workpiece moves through fixed stations. Each station removes a defined amount of material in a defined sequence. The system produces finished engine blocks at a rate no individual machine can match is Ingersoll's principle. The machines that execute it were not made in Rockford. They were made in Italy, in Germany, in Japan. The engineering firms that design them do not have offices on Factory Street. But the discipline they practice, the conviction that precision at volume achieved through a system engineered for a specific purpose, is the foundation of productive manufacturing, is the discipline that Leander Ingersoll brought to Rockford, Illinois in 1887, and that 4,000 workers on Factory Street refined across a century of American industrial history. Ingersoll lost the market. The principle never lost the argument. In a surplus yard on the south side of Rockford, Illinois, less than 2 miles from the building where it was assembled in 1962, there is an Ingersoll transfer line spindle head serial number stenciled in yellow paint on the cast iron housing. The spindle bore is still true. The bearing preload is still within specification. The coolant fittings are still threaded to the original standard. The company that designed it has not existed for more than 20 years. The engine block it once machined, held to 2 ten-thousandths of an inch 500 times per shift on a line that ran 3 shifts a day in a plant that no longer stands, is still in production. Somewhere, in a different country, on a different machine, to the same tolerance. The nameplate still says Rockford, Illinois. That is the only part of the story that has not changed. Every week on this channel, we find the American companies that built the machines. The factory ran on the companies whose names are still on nameplates in surplus yards and tool rooms, and the back corners of shops that have been running the same equipment since the Johnson administration. We tell the story of how those names got there, and why so few of them are still being made. Subscribe if you want to keep hearing them. Leave a comment if you ran one of these machines, or if your father did, or if you know where one is still running. We read every one. The next story is already in the works. It begins in Cincinnati, Ohio. In 1884,